By the end of this journey, you're going to understand exactly how much we've missed and why most of the universe remains invisible to us. Before we go any further, if you find this exploration interesting, a quick like or subscribe really helps the channel grow. Now, let's dive in. When you look up at the night sky on a clear evening away from city lights, how many stars do you think you can see? With perfect conditions and perfect eyesight, the human eye can see about 9,000 individual stars across the entire sky. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. You're seeing roughly 0.00002% of just our own galaxy's stars. Now, extend that thought. There are approximately 2 trillion galaxies in the observable universe, each containing billions or even trillions of stars. The total number of stars has been estimated at around 200 billion trillion, and we can see 9,000 of them with our eyes. This gives you a sense of the scale we're dealing with. But it gets more interesting when we talk about galaxies specifically. While individual stars are too numerous to count, galaxies are the basic structures of the universe. They're the cities of stars, the building blocks of cosmic architecture. Here's where things get strange. We know there are about 2 trillion galaxies out there based on careful observations and mathematical projections. But the number we've actually observed in detail, as of 2025, the most comprehensive galaxy surveys have catalogued somewhere between 10 million and 50 million galaxies. Let's be generous and say 50 million. That's about 0.0025% of all galaxies. Put another way, for every galaxy we've observed in detail, there are roughly 40,000 we haven't looked at yet. If the universe were a library with 1 million books, we've read about 25 of them. And we're trying to understand the entire story based on those 25 books. Now, you might wonder why this is the case. We have powerful telescopes. We've been studying astronomy for centuries. The answer comes down to a combination of factors: time, technology, and the sheer scale of the task. Consider the size of the sky. The entire celestial sphere covers about 41,000 square degrees. The most powerful telescopes, like Hubble or James Webb, don't look at the whole sky at once. They look at tiny patches. The famous Hubble Ultra Deep Field shows about 10,000 galaxies in an area covering about 1/13 millionth of the entire sky. If the entire sky were the size of the United States, the Hubble Ultra Deep Field would be about the size of a tennis court. And it took Hubble hundreds of hours of exposure time to capture that single image. This is the fundamental problem. To see faint, distant galaxies, you need to stare at one spot for a long time. But the sky is enormous. There are millions of these patches, and we can only look at them one at a time. Second, there's the issue of technology and resolution. Not all observations are created equal. You can detect a galaxy, meaning you can see that something is there, a faint smudge of light in your image. But detecting it and observing it in detail are very different things. Detection might tell you a galaxy exists, and roughly where it is. But to really understand that galaxy, to know its distance, its composition, its age, its structure, you need spectroscopy. You need to split its light into component wavelengths and analyze the patterns. And spectroscopy takes time, a lot of time. The Sloan Digital Sky Survey, which ran for years and produced one of the most comprehensive maps of galaxies ever made, obtained spectra for about 2 million galaxies. 2 million sounds impressive until you remember there are 2 trillion galaxies total. That's 0.1%. 0.1% of all galaxies have been analyzed spectroscopically. Most of what we count as observed galaxies are photometric detections, broad imaging, where we can see that something is there and maybe measure how bright it is and what color it appears. But we don't have detailed information. Think of it like this. Imagine you're trying to understand all the cities on Earth. Photometric detection is like flying over a city at night and seeing lights. You know there's a city there. You can estimate roughly how big it is based on how much light you see. But you don't know what the buildings look like, what language people speak, what the culture is, what industries drive the economy. For that, you need to land, walk around, talk to people, study the place in detail. That's spectroscopy. And we've only done the equivalent of detailed ground visits to about 2 million cities out of 2 trillion. The rest are just lights seen from an airplane. Third, there's the issue of distance and faintness. The universe is expanding. Light from distant galaxies gets stretched as it travels, a phenomenon called redshift. The farther away a galaxy is, the more its light is redshifted into longer wavelengths. Very distant galaxies have their light shifted so far into the infrared that optical telescopes can't see them at all. You need infrared telescopes like James Webb, and even then, the light is incredibly faint, reduced to just a handful of photons. Detecting them requires long exposure times and extremely sensitive instruments. Now, let's talk about what we mean when we say observable universe. This term confuses people because it sounds like we're talking about what we've observed, but that's not what it means. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light travels at 300,000 kilometers or 186,000 miles per second. So light from very distant regions hasn't reached us yet. Here's where it gets tricky. The universe has been expanding while that light was traveling. When you account for expansion, the edge of the observable universe is about 46.5 billion light-years away in every direction, making the observable universe about 93 billion light-years across. Everything within this sphere is potentially observable. The light exists. We could, in theory, build telescopes powerful enough to see all of it, but we haven't. Most of the observable universe remains unobserved. The light is passing by Earth right now, but we haven't captured it yet. This is what I mean by the invisible universe. It's not a mysterious dark realm beyond our ability to see. It's simply the part we haven't looked at yet. Let me give you a specific example. In 2025, astronomers using James Webb announced the discovery of over 1,700 groups of small galaxies in the early universe, less than 1 billion years after the Big Bang. They're incredibly far away and faint. Before Webb, we didn't know these galaxies existed. The light from these galaxies has been traveling for over 13 billion years. It passed by Earth countless times, while humans evolved and built civilizations. But we didn't see it, because we didn't have sensitive enough infrared telescopes pointed in the right direction. This discovery revealed something surprising. These small galaxies appear to have played a major role in reionizing the universe, a crucial phase when the first stars formed and their radiation ionized the hydrogen gas-filling space. Before this, astronomers thought larger galaxies were responsible. But Webb's observations suggest small, faint galaxies might have been the main drivers. This shows that what we haven't seen isn't just more of the same. It contains surprises that challenge our understanding. Let's talk briefly about how we got here. In the early 1900s, we didn't even know galaxies existed beyond our own. Astronomers saw fuzzy patches called nebulae, but didn't know what they were. In 1920, there was a famous debate about whether these spiral nebulae were small objects within the Milky Way or distant island universes. Then in 1923, Edwin Hubble resolved individual stars in the Andromeda Nebula and measured its distance at about 900,000 light-years. This proved Andromeda was a separate galaxy. Suddenly, the universe got much bigger. By the 1950s, photographic surveys had catalogued thousands of galaxies. The 1990s brought the digital revolution with CCD cameras, far more sensitive than film. The Sloan Digital Sky Survey obtained spectra for about 2 million galaxies by 2025, providing detailed information about distances and properties. But SDSS only covered about 1/3 of the sky, and its depth was limited. Hubble Space Telescope, launched in 1990, revolutionized our view with deep field images revealing thousands of faint galaxies. Based on Hubble observations, astronomers initially estimated 100 billion to 200 billion galaxies. Then, in 2016, using mathematical modeling, they revised the estimate to about 2 trillion galaxies. That's 10 times more than previously thought. Why? Because Hubble couldn't see the faintest, most distant galaxies. When astronomers accounted for these statistically, they realized the universe contained far more galaxies than we'd observed. Enter James Webb Space Telescope. Webb launched in December 2021 and is an infrared telescope designed to see light that Hubble can't detect. With a mirror 6.5 meters, or about 21 feet across compared to Hubble's 2.4 meter or almost 8-foot mirror, Webb is much more sensitive. In its first few years, Webb has found galaxies from just a few 100 million years after the Big Bang, challenging our models of galaxy formation. In 2024 and early 2025, the Euclid space mission started releasing its data. Euclid is designed to map billions of galaxies across a large portion of sky. In its first year, it catalogued 26 million galaxies in deep field observations. As Euclid continues, it will observe billions of galaxies. But even billions is still a small fraction of 2 trillion. We've made incredible progress, but we've still only scratched the surface. One reason is telescope time. There are only a handful of world-class telescopes capable of observing faint, distant galaxies. They're in constant demand with fierce competition for observing time. There simply aren't enough telescopes and hours in the year to observe everything. Another challenge is observing faint objects. Galaxies far away appear incredibly faint. Their light spreads out over an ever-increasing sphere. By the time it reaches us, a distant galaxy might emit just a few photons per second, hitting our telescope. To detect such faint objects requires long exposure times, dark skies free from light pollution, minimal moonlight, and perfect atmospheric conditions. There's also cosmic dust. Dust in our Milky Way blocks light from distant objects. About 10 to 20% of the sky is obscured by the Milky Way's disk, a region called the zone of avoidance. We can't see distant galaxies through it at optical wavelengths. That means about 10 to 20% of the universe is hidden by dust in our own galaxy. Let's talk about what kinds of galaxies make up the invisible universe. You might think they're just copies of galaxies we've already seen, but that's not true. There's a bias in our observations. We tend to see the brightest, largest, most massive galaxies because they're easiest to detect. A giant elliptical galaxy with 1 trillion stars is much easier to spot than a dwarf galaxy with only a few 100 million stars. But dwarf galaxies are actually far more common. Most galaxies in the universe are small. We know this from studying nearby galaxies in our local neighborhood. In the local group, which includes the Milky Way, Andromeda, and about 80 smaller galaxies, most members are dwarf galaxies. If this ratio holds across the universe, then the vast majority of 2 trillion galaxies are small, faint dwarfs that are very hard to detect at large distances. Dwarf galaxies matter because they're the building blocks that merge to form larger galaxies. They contain clues about dark matter. They might host unusual types of stars or black holes. The Milky Way itself is constantly consuming dwarf galaxies. The Sagittarius Dwarf Elliptical Galaxy is being torn apart by our gravity right now, its stars streaming out into long trails. The Magellanic Clouds, visible from the southern hemisphere, are also being disrupted and will likely merge with the Milky Way in the future. There's a special class called ultra-faint dwarf galaxies that are even more extreme. These tiny satellites contain only a few thousand stars compared to the Milky Way's 100 billion. Some are so dim that the entire galaxy is fainter than a single bright star. We know of about 60 ultra-faint dwarfs in our local group, but theoretical models suggest there should be hundreds or thousands orbiting the Milky Way alone. And that's just in our neighborhood. Across the universe, there are probably trillions of these ultra-faint dwarfs, contributing to the galaxy count, but remaining undetected because they're too dim. There's also the question of entirely new structures. In 2024, astronomers announced the discovery of the Big Ring, a massive circular arrangement of galaxies about 1.3 billion light-years across. According to our understanding of cosmology, the universe should be relatively uniform on very large scales. There shouldn't be structures this big. Yet there it is, along with the giant arc, another huge structure. These were invisible until recently, not because we couldn't see the individual galaxies, but because we hadn't mapped enough to see the pattern. Let's think about the future. What will it take to make more of the invisible universe visible? The answer is more powerful telescopes and better technology. The Nancy Grace Roman Space Telescope will launch in the late 2020s with a field of view 100 times larger than Hubble's. Roman will observe hundreds of millions of galaxies across thousands of square degrees, giving us a much better sense of cosmic structure. On the ground, the extremely large telescope is being built in Chile with a mirror 39 meters or 128 feet across, making it the largest optical telescope in the world. The ELT will see fainter objects in greater detail than any current telescope. The square-kilometer array being built in Australia and South Africa will be the most sensitive radio telescope ever constructed. It will map neutral hydrogen gas in galaxies, revealing invisible reservoirs of gas from which future stars will form.